Last technique of this chapter actually, I think, almost belongs in the next one because it's not as precise as the others. But it's called Chernoff faces. Chernoff is a psychologist, not necessarily a visualization person. So if you search for him, you see, I think he works one of the Ivy League schools. I want to say in California. But he's a psychologist. And his idea was, if I have to show a lot of, again, remember, we're in the point at the point where we're looking for a lot of dimensions, more than 3, more than 4. How can I show a lot of dimensions of the data? And his idea was, what if I use human faces? Why? Because we evolve over time and we can identify shapes, and human faces are, we see people are sad or happy or based on their facial features. So that's kind of the idea here. If I use facial features, it's a very sketchy face. It's not necessarily, I haven't seen them be very accurate, but they're more like a cartoon, but still. And he has done, being a psychologist, he tried it on people, and apparently it works better with faces than with other things. If you do a bar chart, things that are more neutral, scatter plot, things like those. So here are a number of things you could use. It's not exhaustive, and it's not like there is one type of Chernoff face. There's slight variation. Everybody maybe implements them slightly differently. So for the most part, head eccentricity. For example, I have a big head or a small head. I have a really elongated head or a really flat head. So I can have a head that looks like this, or I can have a head that looks more like that. That can show a data dimension, whatever that happens to be. Social security number, I don't know, some data dimension. The spacing between the eye can show a data dimension. Eyebrow slope can show a data dimension. Eye eccentricity also. How big they are, how small they are, maybe even their shape in terms, are they oval, are they round? Pupil size can show something. Nose width, nose length, mouth openness, mouth width, mouth curvature. So all of these can show data. So if you see here, I have 2, 4, 6, about almost 10 data dimension, 2, 4, 6, 8, 10, 11 or so. So I can show data that has 11 dimensions just by this. And here's how they look like. That's one representation. And then you can see that Rhode Island and Massachusetts, they kind of look the same. New York looks more like Illinois. And this I have no idea what it means, but you can see how things change. New Hampshire, Vermont, and Maine, they also kind of look the same. They're from the same region. So you kind of get an idea what you can see clusters also, can see groups that look the same. Maybe you remember them better. So that's one Chernoff face. Here's another Chernoff face. This is from Tufte. This one actually is a combination of the spatial substrate now has axes. So it's a scatter plot. You can see there is a little bit of correlation. So most things so whatever these 2 dimensions are, they tend to be slightly correlated. And then you can see that there are some Chernoff faces that don't belong where they currently reside. This one here maybe smiles too much versus the others. There's a cluster in here. There's another cluster here, and then there's kind of one sitting there. It doesn't look like it's part of that cluster because it has a different shape on the head. So that's what this will kind of do to you. Now, before I kind of finish the chapter, I'm not going to stop recording, but here are 2 kinds of differences that maybe we ran into. So consider star plots and Chernoff faces. Chernoff faces look like this, or maybe an even better representation would be like that. Here is star plots. I'm just going to jump straight to it. What's different? Well, these are similar in a way, if you think about it. How are they similar? And on the other hand, how are they different than parallel coordinate plots and something like Attribute Explorer or Easy Chooser? Here's parallel coordinate plot. Or maybe this one looks better. So how are they different? Parallel coordinate plot and star plot. Well, if you think about it, a star plot shows each object pretty neatly. So if I look at each car individually, I can see all its features at once, grouped together. If I look at a PCP, I cannot see individual objects. And if I look at Chernoff faces, again, all the features about New York are in the same place. So it's like the axes, the attributes are not as clear as the objects. So that is called object visibility. So basically here I can more easily compare objects than in the other one, in Attribute Explorer or in parallel coordinate plots. Those make it easier to compare dimensions or attributes. So they're called attribute visibility versus object visibility. So here I can see how a dimension behaves a lot better than individual plants, individual flowers in here. So it is attribute-centric in the sense that I can see what happens between attributes, not as much what happens between individual plants. It's kind of hard to group them on clusters or anything like that. I can see there's some distribution per attribute. Here I have two sets, but I don't know which sets are they. While if I look at object visibility, here I can find an entire set that looks the same, behaves the same, like I was just pointing out these two, for example. They look the same. New York and Illinois, they look similar. It's hard to compare individual things, individual attributes, but it's easy to compare individual items, objects. So object visibility versus attribute visibility, that is in the book. Somewhere in chapter 3, you're going to run into it. The other thing, if you consider star plots, parallel coordinates, even I can add to it histograms versus something like visualization of relevance, Chernoff faces, maybe even magnet, dust and magnet. How are they different? Again, that's my opinion on them, but here is what tends to happen, and I think it's where these were generated. So a histogram, a Taki box, they come from statistics, and one fear statisticians have is bias. They don't want to be biased. So for one thing versus the other. So over there, they try to give you very unbiased views, and which are, for the most part, kind of boring. Scatter plots are the same. They try to give you unbiased views. They don't say one dimension is more important than the other. They all kind of get the same fair share at representation. If you look at Chernoff face, which dimension is the most important here? Which thing you're going to notice first? It's the size of the head. Now, the size of the pupil may be the worst, or how big the nose is, not going to make that much of a difference. So in a way, you are really, if you're using a Chernoff face, you're not going to be unbiased. You already decided whichever attribute you put on the head size or head shape, that's going to be more important than pupil. That's it. I mean, you already made that decision. So this tends to be less. They don't come from statistics. They're more, they have their own advantage. Same thing here. Here the problem is that your search, the bars determine what you see. So it's not going to be unbiased. If you look from one side, if I go on one side of this room, I'm able to see the backs of all the computers. If I go to the side of a row, I won't be able to see the backs. All computers will look like one, smashed into one, because they're kind of one behind the other in 3D space. Dust and magnets, the same thing. They even have a feature in there. You can make some magnet bigger than the other. Or if you add a magnet later, it has less influence. The ones that was added first actually pulls up a lot more than the last one that you add. So the other thing you do here is the position of the magnet. So there's a lot of bias in this environment. You know what you want, you know where you put your magnets, and that decides a lot of how the visualization looks like. Okay, so again, my 2 cents, visualizations that tend to be more statistic in nature, they would be less biased. The designer, whoever builds the visualization, doesn't have to make that choice. All the other ones, and I think they tend to be cooler, the ones that are more biased. The designer has more choice. They need to make a choice. This is the most important representation. So I would give it more attributes. And I would give it a bigger magnet, or I would put it on top, and all the other ones would be somewhere else. So that's kind of my analysis of this whole visualization. And we looked in this set of slides mostly at data, numerical data. So where we have, how do we represent data with numbers, quantitative